So the next natural progression was to, well, we were missing half the cycle. That kind of sucks. So what we decided to do is we're going to put a second diode in there. And this circuit works as long as you've got a center tap on your transformer. So the transformers we have in the lab, you guys did that lab this week, and we can split up the secondary windings and we can make what's called a center tap. So this is a center tap. And what it does is we used to have 12 volts, but now because we have two after another, it kind of almost gives us 24 volts. RMS, all right? Now the penalty is it's in a transformer, it's real simple. If you're stepping down a voltage, you get less voltage but more current because power is the same on both sides. It's always the way it works. If you get more voltage, you get less current. Okay? So when you're using a transformer, power going in is the power going out, and what you're doing is when going one side to the other, you're exchanging your voltage capacity for current capacity, which you never get more power. Got it? So in this case, because we go to 24 volts, well, we got to expect that we're not going to be able to draw as much current. If we go back to 12, we get more current. Right. So in this particular device, if we give it a shot, I'm going to put the phase dots here. So this is positive here, and positive on that side. So when this is positive, negative, this is going to be positive, negative, and this is going to be positive, negative. You see how this particular spot right here can be both positive and negative depending on what you're referring to. It's positive with reference to this one, but it's negative with reference to that one. Just to mess with you. So let's say on the positive side of things, well, current is going to flow through this diode. It's going to try to come back over here, but it can't because this diode's reverse bias. So this diode in this case is off, and this one is on. Works out good. And current will come through here. And of course, it won't go down here because it can't go this way in the diode. So it finds itself going here, goes to ground. Now, ground is just a designation point. You could call it pizza. You could call it Hellcat engine. You can call it whatever you want. Yeah, they got these nice Hellcats in the Dodges now. I think they put up quite a bit of horsepower. That's another subject. So this is tied to this. So basically the current is actually going back to the transformer. So the only half, we're using this winding here on the positive cycle to feed. So what you get is the first bump. Okay? On the following transition, so when we go negative, like so when this flips over and it goes negative, positive, well, everything flips over this way over here, so this becomes negative, this becomes positive, this becomes negative, this becomes positive. And now the currents, so the currents now are going to flow, this current's going to go this way, this becomes on, and this becomes off, because we're trying to push current that way, and that doesn't work. We can't push against that diode. Can't do it. But we can conduct current this way, so this is no longer like this. The current now comes here. Can it go over there? No, it can't. But it goes through here again, comes back through the ground, and then recirculates over here. So for the other half transition, we use the other side, the other half of the transformers, secondary. Then we go through the other diode, so we get on the other one, we get our bumpity bump. And so on. So we get full wave rectification, which is perfect. Now we've managed to take a sine wave, and we've managed to take this part over here and flip it so it becomes positive voltage. Now, guess what? If I turn the diodes the other way, I could produce negative DC voltage. Good? So you can make negative DC power supplies too. If you need negative voltage, you flip the diodes the other way. Okay? Yes?
What could you need negative voltage for? Where are you going to get that there?
I was gonna do some little bit of acting. I won't do it.
Okay.
Okay, I'll give you a perfect example. Let's say you buy yourself a new car stereo. What's so funny about Peru? Oh, did you need mouth off? Then leaf fan mouth off again? Yeah. Okay, you got a car stereo, right?
Yeah.
Well, in the stereo, there's 2 voltage rails in there. And so they'll have a positive DC and they'll have negative DC so that they can produce your music, which goes up and down like AC. Coming out the speakers is AC. So you can have an amplifier system where you need to have the voltage going from positive DC to negative DC. So you're going to need some negative DC to be able to swing it over.
Okay.
So that's where they use it. Now, in a car system, which is kind of interesting, there's other things going on. They take 12 volts from the battery, and a lot of stereos, like I know what's real common, in the amplifier, they'll have a plus 70 volts DC and a negative 70 volt DC. Okay, you want that, the boom, boom, boom there?
Yeah.
Well, to get the boom, 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 you need a lot of power, so you're going to need some DC going one way or the other.
Okay.
So they have like DC to DC converters in these things. They use switching power supplies, which is another topic altogether.
Yeah.
But that's when you're going to use it. That's one place. Okay. So yeah, in most audio type of stuff, there's always a negative rail.
Yeah.
And that's because if you start getting into transistors, the topology of that thing, they have these things called push-pull amps. So you need positive, you need negative. Not all the time, but it works really good.
Okay.
Okay. So now we've got this thing. So the same deal again. We can come up with, well, we've got a voltage peak here, but this time voltage peak, what's it going to be? Well, let's see. You lose one diode. All right. So let's say I had 24 volts RMS here. Let's say I had 24 volts RMS. So let me put 24. So right before the diodes, 24 volts RMS. What's the peak voltage going to be? Well, it's going to be 24 volts RMS times the root of 2. So what does that give us for a peak voltage? Figure that out right now. 33. So you have 33.94, and every time this thing goes through, you lose 0.7 volts. So this thing over here on this bump is going to be about 33.94 minus 0.7 volts. So 33.24 volts is going to be your peak. So right? So you only lose one diode when you're only using one diode at a time. All right? Okay, now, as far as voltage DC, or the average voltage DC, which is the same thing as voltage average, well, it's basically the same thing as last time, but double. So if you take, so they're going to say voltage DC is going to be equal to 0.318 times 2 times voltage peak, all right, roughly. So you're going to go 2 times 0.318. So they might use like 0.697, 0.696 around there, times the voltage peak, which is 33.24. And that's going to give you
21.14.
So 21.14 volts DC. Okay. And this thing, by the way, is about, it'd be 0.9 times voltage RMS. So this thing is about 90% of RMS. That's the other thing they tell you. So the average voltage is usually about 90% of what voltage RMS would be. Just for you to know. All right? So we're going to do the same thing we did last time. We're going to put a capacitor on this thing. So if we put a capacitor, the same thing happens here. You get charging and you get discharging. So you get this business. This thing like that, like that, right? You get that business going on. So the output is going to look But now there's a difference, okay? The ripple is no longer at 60 hertz. The ripple is at 120 hertz, okay? Because we don't have that gap anymore. So if you take a look at the period for this thing right here, it's like 8.3 milliseconds. And if you do 1 over that, you're going to get 120. Okay? So ripple now on these types of things has doubled. Okay, now we have one last thing. We have a little formula for ripple voltage. So the voltage, the ripple voltage peak to peak. So this ripple voltage, V ripple peak to peak. If we want to calculate that, or a rough calculation, it's going to be I load over, I believe, frequency times capacitor, right?
Yep.
So let's figure that out. So let's say in this case, let's say I figured out my voltage DC. So if I want I load, I'm going to take my voltage DC that I calculated and divide it by 100. So 21.14 volts divided by 100, and I get 0.21 for 211 milliamps, right? Does that work out? Everybody check my math to make sure. I'm pretty sure it's pretty much.
Yeah.
So that should be my load current. So the current going through here is roughly about 211 milliamps. Everybody sees that? So if I want to figure out this ripple thing, I go, all right, let's say I've got a capacitor over here and I put a capacitor of 100 microfarads. Well, I would say, well, I load is about 211 milliamps divided by frequency is 120 hertz times capacitor is 100 microfarads. So my voltage, my ripple voltage, so you guys figure that out, to 0.211 amps divided by 120 times 100 microfarads. And that should give you something in millivolts.
17.58.
How much?
17.58.
Millivolts?
No.
Oh, I think so.
Yeah, so there is, we have to.
17 volts at ripple? Man.
17.6 millivolts.
This is milliamps, we have to do it times 1,000 or divide by.
Yeah.
So that's roughly the ripple right there. So you've got this little ripple, you got a DC voltage with about a 17 millivolts of ripple riding on top of it. And of course, you put a bigger capacitor, ripple goes down.
It's not okay.
Any questions so far? No? Okay, so it brings us to our last circuit. So the last circuit, what we're going to do is the same idea, but this time we're going to use a bridge rectifier. So the bridge gives us the luxury of not having to have or need a center tap on our transformer. So let's say this is your secondary. And this is where it's important. You got to make sure your diodes are going the right way. So there's ding, ding, ding.
So what was the answer for that last question you did? I didn't write it down quick enough. Anybody write it down?
17.6 millivolts.
Okay, cool. 17.6 Yep. 2.6, yeah.
1,
Oh, okay, well, I forgot to add a zero somewhere.
you're like 175.
Come on.
Okay, I'm going to make this quick and then you can leave. So the math we just did for the last circuit applies. It's the same formulas that apply for this thing because we get the same waveform. At the output, what we will have, if we go over this, so if we take V out on this resistor right over here, our load, we will see exactly the same thing. Badoom, badoom, badoom. Okay? And the difference here is we don't need a center tap on our transformer. If we had our transformer, all we had was one winding, we can do it. And this is the most common thing, all right? This 4-diode bridge business is what is usually seen in linear power supplies. And you can get this thing, like you can do it discretely, you can do it with 4 diodes, like you guys did in the lab, or you can actually buy a component, and like I've got some at home, and it's like a little steel block, and it's got 4 diodes inside of it, and I think mine can handle like 16 amps. Yours can handle 1 amp, but you can buy it for cheap, like they're $2 out of China, and you get a little square type of thing. They're made out of metal. You can put a heat sink on it. And actually this summer what happened is I was working on a piece of equipment, and when I got it, I had a bridge rectifier on it, and it was burnt out because the heat sink had gotten loose, and it was running a lot of current, couldn't dissipate it. Okay? So it was just a matter of replacing it and putting another one and making sure it's like tied to the chassis really good so that it can dissipate heat. Anyway, so the way this thing works is very simple. So when phase dot here, so on the positive transition, so let's do this in green. So the positive transition, this part right here, so the first 180 degrees, positive, negative. Current flows this way, goes in this way, and hopefully returns this way. So let's see what happens. So when current, let's call this node A. So when current gets to node A itself, I'll give these diodes a name. I'll call this D1, D2, D3, D4. All right? So when the current gets to node A, it has a choice. Do I go into D1? No, I can't go into D1 because it's blocking it. I can go into D2. Goes to D2. It gets to node, let's call this B. It has a choice. Do I go down into this thing? No, I can't. So it goes into the resistor. Resistor is tied. This resistor is actually tied over here, so the current comes over here. And then it's got a choice. I can either go D1 or D3. But the thing you have to remember is the voltage up here, the potential up here, this is more positive than this side, so this diode can't conduct. So D1 cannot conduct, because the voltage on this side is higher than the voltage on this side. So the current goes into D3 and then makes its way back to the winding. Okay? So what happens on the positive transition, D2 is on, D3 is on, D1 is off, and D4 is off. So you have 2 diodes that are on, 2 diodes that are off. That means over here, whatever you get here, well, let's say I had 12 volts. Let's say I had 12 volts RMS here. That would mean that my peak would be, what did we figure out a while ago? 16.97 volts, right? So it means the peak over here would be 16.97 volts minus 2 diodes, okay? So 1.4 volts. So what does that give us? 15.93.
93.
No.
15. Yeah, it should probably makes it.
So that's what the peak voltage is here. Okay? Because you lose 2 diodes.
1.4.
And the voltage, so this over here, the voltage DC, is going to be equal to 2 times 0.318 times 15.57. So that'll give us a DC voltage, or average. So you figure that out. On the other half cycle, before I keep going, on the other half cycle, this would be negative, this would be positive, and what happens is the opposite. So on the other way around, it goes through D4, comes out through here, makes its way back through D1. So on the reverse transition, it's the other two diodes that go off, the other two that go on. And every time you're using two diodes. Capiche? Okay, so what did you come up with? 2 times 0.318 times 15.57?
9.9.
9.9. And that would be your DC voltage. From that, you can figure out your load current, and then you can figure out what your ripple would be peak to peak. And again, the ripple is at 120 hertz. Is this stuff clear? Well, that's the whole thing for today. If you have any questions, well, take them up and come and ask them. And that's it. That's all. Now you've got the half wave and the full wave. And the next thing we're going to talk about